So the quotient rule says the derivative of the quotient f of x over g of x is the derivative of f times g minus f times the derivative of g over g of x squared. So let's prove this. There's lots of nice ways to derive this quickly. You can use a trick with the product rule. You can derive it from the product rule together with the quotient rule. But just to see it and to see again some of the ideas in the proof of the product rule come up, some of the geometric ideas, let's prove this just from the definition of the derivative. All right, so it's going to take some work, some algebra, but it's going to look a lot like the product rule. So we're going to let's call it q of x for quotient be f of x over g of x. Okay, and of course, then we're going to take its derivative. So then q prime of x is going to be the limit as h approaches 0 of q of x plus h minus q of x over h. Okay. So there we go. As h approaches 0 of, so q of x plus h is of course f of x plus h over g of x plus h. And q of x is f of x over g of x. And all this stuff is still divided by h. All right. So I'm just going to get a common denominator on top and add everything up, and then I can make this into one big fraction. So to get a common denominator on top, I'm going to multiply the top and bottom here by g of x, the top and bottom here by g of x plus h. So that'll leave me with f of x plus h g of x, so multiplying top and bottom here by g of x, and then over here, minus f of x times g of x plus h. And each of these will be over g of x plus h times g of x. So I'm just going to put them together right now. So g of x plus h times g of x. All right. And of course, all this stuff is still over h. Okay. And now moving stuff around a bit. Remember, h is the same as h over 1. And so I can do this flip-flop and multiply. So I'll have f of x plus h times g of x minus f of x times g of x plus h on top. And, you know, after taking this and doing flip-flop and multiply on here, h times g of x plus h times g of x. I guess these parentheses, extra parentheses are unnecessary, but whatever. Okay, so now what I'm going to do is I'm actually going to move these two g's out here. So I'm going to separate this into a product of two things. And I'll show you why I'm going to do that in a sec. You'll see. It's going to be the product of this guy and this guy. So I'm going to move the g of x plus h and g of x over here, and just leave the h here. And I'm just going to put a 1 here and leave the numerator up here. So f of x plus h, g of x minus f of x, g of x plus h. Okay, so why am I going to do this? Well, basically because this thing is going to be my g of x squared in the denominator. So that's actually kind of taken care of here. So I've got g of x plus h times g of x, but h is going to go to 0. So I'm thinking, okay, this is going to be my g of x squared. And so this is just going to be the numerator, so I'll work on this guy over here. So let's do that. Let's split this up into two limits. The limit of all this stuff times the limit as h goes to 0 of this f1 over g of x plus h g, whoops, times g of x. Okay, so this is still the same. g of x minus f of x times g of x plus h over h. So remember, limit laws say we can do this. The limit of a product is the product of the two limits as long as both of these exist. So this one, let's call this limit number 1, we're going to do on the next page. But notice that this guy, what is this? Well, in fact, I could pull this g of x out front if I like. It doesn't involve h. The only thing that involves h is this g of x plus h right here. And as h approaches 0, this h is going to go to 0. Then this g of x plus h is going to get closer and closer to g of x plus 0, which is just g of x. And so as long as g is continuous at x, then the limit as h approaches 0 of g of x plus h is just going to be g of x, because I'm approaching x by letting h get really close to 0. X of x plus h is getting really close to x. And so as long as g is continuous, then the value I get when I approach x is the same as the value I get when I plug in x. So g of x, the limit of h approaches 0 of g of x plus h will just be g of x. So this limit is just 1 over g of x squared. Okay? Because this h goes to 0, and as long as g is a continuous function, which we're going to see, remember that we want to take the derivative of g of x in this formula, so it better be differentiable at x, and so therefore it's also going to be continuous as long as it's differentiable. Great, so this limit right here ends up just being 1 over g of x squared. So now in here, we got this one to deal with. So I don't even have to give it a number because it's the only one left. So the question is, what is this? And now is a good time to pause the video and see if you can figure out this. We're going to use exactly the same idea as in the product rule proof, if you've seen that. So we're going to interpret these products as areas, and that's going to let us evaluate this. So here we go. So let's draw a picture just like we did in the product rule, where we've got these two quantities, f of x plus h, f of x, g of x plus h and g of x, just like I did in the product rule. Okay, so let's just do one here maybe, and another one, I don't know, here. Okay, so suppose that this guy is g of x, and then maybe as x gets a little bit bigger by h, g also gets a little bit bigger. Here, f of x, and then again, as x gets a little bit bigger by h, let's suppose that f also gets a little bit bigger. Now looking at this guy right here, I've got f of x plus h times g of x. So f of x plus h, this guy right here, and g of x, this guy right here. So shading that area this way, this shaded area right here, that's this term right here, f of x plus h times g of x. F of x plus h times g of x gives me the area of that rectangle. Similarly, for this term, f of x times g of x plus h, it's f of x and g of x plus h. So I'm going to shade that this way. And so, if I take the difference, this one minus this one, then I'm counting the area shaded this way as positive and the area shaded this way as negative. So if I do the area shaded this way minus the area shaded this way, this region cancels out because it's counted once positively and once negatively. But this region, number 1, gets counted positively. This region, number 2, gets counted negatively. So now rewriting this guy right here, I've got the limit as h approaches 0. And so this difference is just area 1 minus area 2. So here we go. What's area 1? Its height is this guy, f of x plus h minus f of x, and its width is g of x. So its height is f of x plus h minus f of x, and its width is g of x. So there's its area. That's the area. That's the area of region number 1. And that's counted positively when I do the difference here. And now this area is counted negatively, so it's going to be minus, what's this one? F of x times this length right here, g of x plus h minus g of x. It's g of x plus h minus g of x. Okay, and all of this is over h. And I'm going to put this in a big pair of parentheses, because remember, hanging out on the end here, I have this limit, which turned out to be 1 over g of x squared. So I have this 1 over g of x squared hanging out over here now. Good. All right, and now you can see we're almost done. We have the derivatives of f and g waiting in here. This f of x plus h minus f of x and h. So we're just going to move stuff around and, yeah, split this up into 2 and move stuff around, and we should be good. Let's do it in 2 steps. Here, limit as h approaches 0 of, break this up, f of x plus h minus f of x times g of x all over h minus the limit as h approaches 0 of f of x times g of x plus h minus g of x over h, still multiplied over here by 1 over g of x squared. All right, so I just broke this up into this difference of limits into, this limit of a difference into the difference of 2 limits, just using the sum law for limits. So that's using limit laws, right? As long as these limits both exist, I can do that. And let's see what happens here. We are now almost done. This g of x, it does not involve h, so I can pull it out. So I've got g of x times the limit as h approaches 0 of f of x plus h minus f of x over h. And there it is. That's the derivative of f. Minus, now I'm going to pull out the f of x here, times the limit as h approaches 0, g of x plus h minus g of x over h. There's the derivative of g. And this whole thing was times 1 over g of x squared. All right, so remember, this guy is called f prime of x. This guy is called g prime of x. And remember that when I write this, I'm assuming that these limits exist. Like, this is f prime of x as long as, like, this limit defines f prime of x, which is going to give us a number as when this limit exists. And similarly here for g. So I just want to point out that in writing this formula, in writing g prime of x, for that to actually give us a number, we're assuming g is differentiable at x, which, as I mentioned before, implies that it's continuous. And so back when we used the continuity of g to evaluate this little guy, we weren't assuming anything extra. In order for this formula to make sense, we want g and f to be differentiable. Otherwise, these two terms, they won't give us real numbers, and this formula won't work. Okay, so finally, what do we have? Writing these in the opposite order. F prime of x, g of x, minus f of x times g prime of x, multiplied by 1 over g of x squared. And there it is, there's the quotient rule. So just writing it as one big fraction, we have f prime of x times g of x minus f of x times g prime of x over g of x squared. So there's the quotient rule.